Okay, so it's 5:10, so I think we can just go ahead and get started now. So, hi everyone, welcome to the Thursday problem set review. So we'll be going through problem set 12, problems 1 through 4. I'm gonna send the approximate schedule in the chat right now. So yeah, with that said, let's just go ahead and get started with question 1.
Hey, can everyone see my screen and hear me?
Yep.
Yes.
Yep.
Okay. Let me just present this real quick. Okay, so I'm just going over the conceptual review for problem 1. So in this question, we're basically talking about rate constants K. So basically, we're describing this reaction A. Also, are you seeing the slide view or the full screen view of the slides?
We can see both your current slide and your next slide.
Oh, okay. Let me switch my shared screen. Sorry. Just gonna stop sharing for a sec. Sorry, just so that everyone can see the screen properly. Okay, is it full screen now?
Yes.
Yep.
Okay. All right, yeah, so we're basically looking at a reaction that goes where you have some arbitrary coefficient A, lowercase a, plus some reactant A, plus another arbitrary coefficient B, with the reactant B that goes to some other product. You could have multiple products, but ultimately your goal is to figure out what the change in concentration of the reactant C over time is, which is your rate. And we know from like the basic kinetics that we learned in lecture that it's equal to this rate constant K times the reactants to some certain power, X and Y. And these X and Y, we don't know them. It's impossible to know them like a priori. Like you have to determine these X and Y experimentally. They could match the A and B here, but they don't necessarily. So you have to keep in mind that this is different from like the thermodynamics. When you're studying thermodynamics, you can use the coefficients of the reactants to make statements about the delta H to delta G. Whereas with kinetics, these rate coefficients, the coefficients, the stoichiometric coefficients have no relationship whatsoever with the kinetic rate law. And so these X and Y terms here are also what you, so if X or Y were, if X was 1, you would say that this reaction rate is first order with respect to A. And if Y is 2, you would say it's second order with respect to B. But regardless, you still have to determine what X and Y are based on the data. And so one way that you can do this if you have multiple reactants is you can compare 2 different rates at 2 different concentrations. Like if, say you wanted to figure out with what respect it is to B, you could hold the concentration of A equal. So you'd set A1 and A2 equal, and then vary the concentration of B and see how your rate reactions, your R1 and R2 change so that you can calculate what the order is with respect to B. But that's just one specific example. I'll be going into more detail, like what 0, first and second order are. So for most of the problems that you're going to be solving with, I would definitely recommend referring to this table. You can see that the 0th order reaction is a rate where the rate is equal to K, which is some constant. So basically, it's not related to the concentration of your reactants at all. So if you're testing out a 0th order reaction, you would graph your concentration versus time, and you would find that it's linear. This is the kind of graph you'd get going from that. You'd find that you'd have a constant conversion of A to B. It doesn't depend on the concentration, and it's just a linear slope. So there's this idea that I mentioned on the previous slide, which is the half-life. And the half-life is basically the time at which the concentration is equal to half of the concentration that it was initially. And so if you look here, if you start out with 0.2 moles per liter as your concentration, and then you end up with 0.1, that the time at which that occurs is the half-life. And so then if you want to compare the next half-life, you look at when it's half of 0.1 moles per liter. And so you look at 0.05 here. And so you'd see that the amount of time is significantly smaller in a 0th order reaction. And so since it's a linear process, it should basically always take half as long to go from A naught over 2 to A naught over 4 in this case, and it'll constantly keep going down that trend. And so that's one way that you can use the half-life of your, like whatever you're given in the problem, to calculate whether or not this is a 0th order reaction. Any questions about 0th order reactions before I move on to some of the other ones?
Yeah, I'm just wondering, but are these slides with the table, for example, going to be provided on Piazza or no?
I can upload them on Piazza if you'd like, yeah.
Right, thank you.
Yeah, I think this lecture is also being recorded, so you can view it that way as well too. But
Right.
this table especially you can just find with the quick Google search, but I'll upload the slides as well too. Okay, if there aren't any other questions about that, I'll move on to first order. So first order, you can see that the rate is equal to K times the concentration to the first power. And if you're trying to solve for what the half-life, if you're trying to solve for the half-life, in this case, you would plot log of A, the natural log of A versus T, and you'll find that that graph should have a slope equal to negative K. I'll show an example of that here. So this is the first order reaction. You find that it's basically an exponential curve, and you'll find that the half-life is always constant. So if we originally start out with 0.2 moles per liter here, and by the time it reaches 0.1, it's taken this much time. If you check when it's equal to, when it's 1/4, which is 0.05, it's taken this much time, which is the same amount of time. And so you'll see that the half-life remains constant. And if you look back at the expression here, it's equal to, the half-life is equal to, this is the natural log of 2 over K. So if you look at the integrated rate law, you can basically plug in A over T over, the concentration A of T over A naught, and that's where this 0.693 comes from. If you want more details about where that comes from, you can ask private message me afterwards and I can explain. But you'll find that overall the half-life remains constant, and that's an easy way to tell that it's a first order reaction because of that, and then it should follow an exponential fit as well. Any questions about first order reactions? Okay, if not, I'll lastly move on to second order and higher order reactions. So you'll see that it's equal to K times the concentration squared. The integrated rate law is a little bit more different, and in order to figure out what K is exactly, you can use, you can plot 1 over the concentration versus T, and you'll find that that should have to be a straight line with slope K. This is roughly what it looks like on this slide here. You'll find that the half-life ends up increasing over time because it's a much faster drop-off than it is with the first order reaction. So you can't really necessarily say with second and higher order ones whether or not it's like definitely doubles or something, but you'll find that it increases, and then you can plot this graph to find K, and then you can just basically follow the instructions within it here. If you have to test for higher than the second order, I highly doubt you'll have to do that on a problem set or exam, but just in case you need to, this is the following rate law that you follow. Any questions about second order reactions? Okay, if not, we can move on to solving the problem itself.
All right, let me get my screen ready. Okay, can everyone see my screen? I'll just shout it out.
Yes.
Yeah, okay. So I'll be going over question 1. So question 1 compares 2 different reactions, reaction A and reaction B. And part A asks what is the order of reaction for reaction A and reaction B. So to understand these reactions better, we can graph them. And specifically, we can graph the concentration of reactants or the fraction of reactants remaining as a function of time. And then from this, we can determine how the rate of reaction depends on the amount of reactants present at a given time. So for reaction A, it's half complete in 20 minutes, and then it is 75% complete in an additional 10 minutes, which means that 25% of it is remaining at the 30-minute time point. So from this graph, we can see that reaction A, the fraction of reactants, decreases linearly. So reaction A proceeds with a constant rate, and this tells us that the reaction rate is independent of the concentration of reactant present at any given time. So which order reaction is independent of reactant concentration? Someone can just shout it out.
Zero order.
Yes. Okay, exactly. So since the reaction decreases linearly, we know that this is a zero order reaction. That's that. And then we can do the same thing for reaction B. So reaction B is also half complete at 20 minutes, but at the 40-minute mark, so in an additional 20 minutes, it is only 2/3 complete, which means that 1/3 is remaining at the 40-minute time point. So this means that there's a greater decrease between the 0-minute and 20-minute time point than between 20 minutes and 40 minutes. And so over time, the reaction seems to slow down. So from this graph, we can see that the rate of reaction B does depend on the concentration of reactant present at a given time. And so we can eliminate the possibility of it being a zero-order reaction. So now we can check whether it's a first-order or second-order reaction. And in order to do that, we could look at the half-lives. So to reiterate what Faryaz said, half-life is the time required to convert half of the initial reactant concentration to products. And for a first-order reaction, the half-life is this. The half-life is given by this equation. So half-life is ln2/k, and this half-life is constant, which means that the time required to go from 100% to 50% is the same as the amount of time required to go from 50% to 25%. So for second-order reactions, the half-life is given by this equation. And from this equation, you can see that half-life is dependent on the concentration of reactant present for second-order reactions, and half-life is inversely proportional to the reactant concentration, which means that half-life becomes longer when the initial reactant concentration decreases. So we can see that this seems to be the case with our reaction, reaction B, because in the first 20 minutes, it goes from 100% to 50%, but in the next 20 minutes, it only goes from 50% to about 33% instead of halving again. So in order to make sure that this is a second-order reaction, we can plug it into the half-life equation, and we can plug in our data points. So we can plug it into this half-life equation and say that at 20 minutes, or 20 minutes is the first half-life, and 20 minutes equals 1 over the initial concentration, which we can just say, to make calculations simpler, say is 1 molar times K, and then we can solve for K and get K is equal to 1 over 20, or 0.05 per molar per minute. And so then now that we've determined K, we can plug K into the rate equation, or the integrated rate equation, which is for a second order reaction, A, concentration of A equals the initial concentration over 1 plus A naught KT. And then we can see what we expect at, or what concentration we would expect at the 40-minute time point. So for T, we can plug in 40 minutes. Here we can just use our initial concentration, which we've determined to be 1 molar. And here we can use the K that we determined earlier, which is 0.05 per molar per minute. And so when we do this, we get that the concentration of A that we expect at 40 minutes is 1/3 molar, which is 1/3 of the initial concentration. So this is what we expected if it were a second order reaction. So from this, we can determine that reaction B is second order. Okay, any questions on this part? Okay. So then we can move on to part B, and part B asks, how long will it take each reaction to reach 90% completion? So 90% completion would mean that 90% of the reactant has been converted to product. So 10% of the reactant is remaining. Let me, okay. So for reaction A, we can plug in our data points from the first part to determine the rate constant. So we know that it's a 0 order reaction now, so we can use the 0 order rate equation, which is this. Concentration of reactant equals A naught minus KT. And then we know that 0.1 would be the final concentration. Or, sorry, okay. So I misspoke. We're using one of these data points. So we can use this one. And we know that in 20 minutes, the reaction goes from 1 to 0.5. So if we're starting with 1 molar, for example, we end up with 0.5 molar. So 0.5 equals 1 molar minus K, and then 20 minutes. And from solving this equation, we get K is equal to 0.5 over 20 minutes, which is 0.025 molar per minute. And then now that we have the rate constant for our reaction A, we can plug in this K value to determine the time required to reach 10% of the initial reactant concentration. So we can use the same equation again and say that 0.1 equals 1 minus, for K we use 0.025 mole per minute. And then T is what we're trying to determine. So then after this, we can solve for T. And that tells you how long it takes to reach 90% completion. Now we can do the same thing for reaction B. This is simpler because we've already determined the value of K for reaction B. And so we can plug this in to the rate equation, which I'll just rewrite really quick. And then K is, T is what we're trying to determine. So we're trying to determine this. We know that K is equal to 0.05 per molar per minute. And then here, again, the initial concentration would be 1 molar, and then the final concentration would be 0.1 mole. And so then we can again solve for T, and that's the answer. So are there any questions on this part? Okay. If there are no more questions, we can move on to question 2.
Okay. So I'm James. I'll be covering both concept review and problem solving for question 2. So for my concept review, I'll mainly talk about reaction rate constants, especially K forward, K reverse, and derivation of equations from differential rate equation, and lastly, K on, K off, and K observed in a context of protein binding. So to start off, I'm going to look at the simple reversible reaction where the A is getting converted into B, and the B can also get converted into A. And we define that from going from the A to B, it's going to be K forward, and going from B to A is going to be K reverse. And then from the concept review for question 1, that we know that if you were to write this in kinetics, differential rate equations, the change of protein, the change of concentration of A over in respect to time is going to be negative K forward times concentration of A plus Kr times the concentration of B. And that is because for going from the forward reaction, we are actively removing A, and then the reverse, we are converting the B to A, so increasing the concentration of A. And so also we are interested in the change in concentration of B in respect to time. And here's a little subtle assumptions that are often neglected, but really important, that we assume that there's no addition of A and B during the process. And because we know that just the change in the concentration of B is just basically the negative of the change in concentration of A. So it's going to be Kf times the concentration of A and minus Kr times the concentration of B. And then we can also, lastly, we can get another information from this assumption that if you were to add all the molecules we have for A and B, that's going to be the total in the system. And then this total in the system doesn't change because we are not introducing or removing A or B in the system. So from this relationship, now I want to show you the derivation of integrated rate equations from the first differential rate equations. And if you were to take the integral, then we have to take consideration of variables that we're looking at here. And then we have the concentration of A and the concentration of B. They're both variable. And then if you're taking integral, we oftentimes want to simplify as much as possible to make the calculation easier. And then because of the assumptions that we make here, we can say that we can rewrite B as in terms of total minus concentration of A. So if I were to rewrite this equation, it's going to be delta T equals minus Kf times concentration of A plus Kr is total minus concentration of A. And then if I were to collect likely terms together, it's going to be minus Kf plus Kr times the concentration of A plus Kr times total. This is clear to everyone. Okay. So
hey, James, really quick, there's a question in the chat. Do we assume that the reactions are first order here for
Yeah,
A and B?
so we assume that those are the first order because we have one molecules here, A, and then in the other direction, we also have one molecule. So actively, this is going to be the first order reaction that will be showing here. So now I'm going to take the integral. But before I take the integral, I want to simplify this form even more because having those terms and then you're likely going to make errors, mathematical errors, and so on. And then you see that we have constants here, that KFR and then KR total, they're just basically constant here. So basically only variable that we have is just basically the concentration of A. So I'm going to denote this as a little a, and then this is going to be a little b. So if I were to rewrite this, it's going to be little a times the concentration of A plus B. So now I'm going to do the integration. So d delta A over T equals A concentration of A plus B. And then if I were to bring this right term to the denominator of the left side and then bring the dt on the right side, it's going to be d delta A plus B equals dt. And then I'm going to take the integral on both sides. And for the t, it's going to be from time 0 to a certain time that we're going to take the second measurement where we take the concentration. And on the left boundary, we are starting off by some random initial concentration, and the final, we're going to observe also final concentration, just A, I denoted here. So here, if I were to take integral, for the right side, it's just going to be a T. And for the left side, because the form is like the 1 over something, it's going to be a natural log. So natural log ln A, and the concentration of A plus B. And basically, because we have the constant A in front of the variable they're integrating with, by the chain rule, if you were to take the derivative here, you're going to take out A additionally. So we have to get rid of that by having 1 over A. And then the boundary here is going to be from the initial concentration to the final concentration. And then T is going to be 0 to T, which is just basically equal to T. And then I'm going to move the 1 over A to the right side. So multiply A on both sides. And ultimately, it's going to be ln A plus B minus ln A concentration of A plus B. And this is initial equals AT. And then we know the nature of the natural log. We can divide the inner terms if you're subtracting those natural logs. So basically, ln A plus B, A initial plus B is equal to AT. And then I will get rid of this natural log. So I will put, so the right term is going to be e to the AT power. And then I'm going to move this denominator to the right side such that it's going to be A times B to AT. And then I'm going to subtract B on both sides and divide by A on all the terms. So in the end, so what we get is the concentration of A is basically the initial concentration that we get plus B over A e to the AT minus B over A. Now we have to go back to the B over A, and what is A? So from the initial assumption, well, we simplified minus KF and KR to be the constant A and the KR times total to be B. So we know that this A term is going to be somewhat, it's going to be observed K constant, and it makes sense because we have KF and KR that are added together. What about B over A? So let's examine what is B over A. So I'm going to put minus B over A and having those minus terms just for the make the calculation easier. And then if you were to use these terms above, is equivalent to KR total over KF plus KR. So here I'm removing the negative sign by having the negative sign in front of B over A. And then let's say this is some random variable that we don't know at this point, but it's going to be clear as we go along. So if I were to multiply the denominator on both sides, it's going to be KR times total equals KF rectangle plus KR rectangle. And then if I were to combine like terms for KR, it's going to be KR total minus rectangle equals KF and rectangle. And from this equation, you should be able to tell, like, this is very similar to what I described in the beginning, the assumption that we made, and then they're subtle but really important. That you see here that we define the B as the total minus A, and then you see a similar form right here, total minus rectangle, and we have a rectangle, and above here we use A. So let's just plug it in. Let's just assume that the rectangle is A and let's see how it looks like. The KR is total minus the concentration of A is K forward of concentration of A. And then basically this one is basically equivalent to KR concentration of B equals K forward concentration of A. And then this expression, this equation here is only satisfied when we are at equilibrium. So which means that those concentration of B and concentration of A has to be the concentration at equilibrium process. So therefore that we know that the rectangle here is going to be concentration of A at the equilibrium stage. So now we know that what is B over A. I'm just going to rewrite this equation here. It's going to be initial concentration plus, so minus here because above here is going to be minus B over A. So it's minus the concentration of A equilibrium e to the minus K forward and then K reverse times T plus concentration of A at equilibrium. So we have this formula, and then this is how we derive this formula. And then it's really important to take a note that we are using the first order reaction. And then the reason why one of the reasons why I'm showing this derivation is because if you were to have a second order or third order, this derivation will be completely different. So therefore you will end up with different equations. So therefore this is for the first order. So now let's look at the protein binding and how they're related here. So usually protein binding, we denote as a protein and we have a ligand and then they form a complex P.L. And we're gonna denote the going to the right side as K on, but it's effectively they're just the same thing as K forward. And then the K off is just basically K reverse. And one of the difference we see compared to the simple reversible reaction I showed you going A to B and B to A is that now we have two molecules here so that the K on here is basically a second order while the K off is a first order. And because we have a second order, we can't really use this formula above. But we can actually make one assumption that if you make the ligand concentration actually bigger than the protein concentration, we can actually consider the forward reaction K on to be pseudo first reaction order. So let's see why that is the case. So if you were to write the second order, it's going to be K on times the ligand concentration times the protein concentration. And then you know that if you make the ligand concentration really high compared to the protein concentration, let's see what happened. We have a protein and a ligand, and then basically they're forming a structure, the complex, meaning that if you're actively removing one ligand, you're also removing a protein and then forming a complex, meaning that you see that if the ligand concentration is really high, if we see the change in protein concentration, the ligand concentration relatively is constant. So the ligand concentration, despite how much we take out, because it has to be related to the amount of protein we're removing, this L is relatively constant. So we're gonna rewrite this as K on prime, and it's gonna be K on times P, the concentration of protein. So therefore it's gonna be pseudo first order. And then because we know this is a pseudo first order, we can use this formula now. So let me just rewrite this formula with the correct names here. So we have protein and the proteins, and then here we have K on and the prime, you have to consider that, and plus the K off. So, and then here is basically the K observed, that the K value that we're going to observe from the protein binding experiment that we're going to conduct in question 2. So we know that K observed is basically K on prime plus K off, and is also equivalent to K on times the ligand concentration plus K off. Okay, so that is it for my concept review, and then I'll quickly jump into the question 2. So here that we do the experiment, the protein binding protein. So we are trying to bind the drug to the protein, and then we have observed rate constant, K observed. And then we know that the drug concentration is 3000 micromolar, and then K off is 0.05 second to the -1. And we want to find the KD. So we are given the K off value, and then we want to find what is KD. And then you know that KD is basically K off over K on. So you need to find K on to solve this problem. And then before we further plan our calculation, let's first look at the graph here. So because the things I described in my concept review is probably going to be first order, but we have to tell from the graph whether this is actually first order. And this is very similar to question 1. So we're going to go from 1, 0 to 1, 3 in this order because it's easier to tell. For the 0th order that we want to see a linear line, which is not the case. So we know that this is not 0th order. And then for the first order, that we know that the first order has a constant half-life. So we want to dissect into 0.5 and 0.25 and then look at their respective time. And then we know that the times are constant. There are 2 seconds. So therefore, we know that this is first order reaction. So since we know the first order reaction, now we can use the formula that I got above here. So what I can do first is find the K observed and then use the K observed to calculate the K on, and therefore finally get the answer for KD. So let's do the calculation here. For the first order, we know the half-life is basically ln2 over K observed for this case. And we know the K observed here is going to be ln2 over 2 seconds. And then we get the answer here in units of second to the -1. And then we know the K observed is basically K on prime plus K off, which is also same as K on times the ligand concentration plus K off. And then we know that for this case, the ligand concentration is the drug concentration. And then we know that drug concentration is really high. So we kind of think that our assumption that the drug concentration is much higher than the concentration of protein. So that's going to be the consumption that we're going to go along here. So K on times 3000 micromolar plus 0.05 second. So here we can find the K on is going to be something, and then in units of second -1. And then we know that it's going to be, we also have a micromolar as units because we need to cancel out these units. And now we know that KD is just K off over K on. And we know these 2 values, and therefore we should get the answer in micromolar. Or if you were to use a different concentration, you need to denote the concentration that you're using. Okay, is there any questions?
Can you scroll up a little bit?
Yeah.
I mean, go to the previous page where you got that formula.
Oh, yeah.
Sorry. Thank you.
This one?
Yeah, thank you.
And then we know that KD is, there's a question whether the KD is K on over K off. It is actually K off over K on. It's reversed. Any other questions? Okay, so we'll move on to question 3.
Can you guys see my screen and hear me? Okay, so I'll be going, my name is Michael. I'll be going over some of the concepts for question 3. So for the first part, it's the first order half-life reaction. And that was gone over in the first question, so I'll be skipping the concepts for that one. The rest of the question is concerned with the Arrhenius plot. So I'll be going over what the Arrhenius plot is and what it can tell you. So the Arrhenius equation can be seen in two forms. The left side is with kBT, which is the Boltzmann constant, and the right side is with RT, which is the ideal gas constant. And the difference between these two is that you would have different units for the activation energy. For the left one, your activation energy would be in joules per molecule, while on the right one, it would be in joules per mole. And then this Arrhenius equation allows you to relate the rate constant of a reaction with a pre-exponential constant, the temperature, and the activation energy. So the couple of key elements here are the rate constant. Oh, whoops. Right. Ignore that unit of rate constant. That's supposed to be for the rate, but the rate constant itself will depend on the order of the reaction. The temperature will be in units of Kelvin. The activation energy will be in joules per mole or joules per molecule, as I said before, depending on whether you're using RT or kBT. And the pre-exponential constant will match the rate constant, so it will also depend on the order of the reaction. So if we look at the exponential term, so this exponential term represents the probability that a molecule will have enough energy to overcome the activation energy barrier. And this probability comes from the Boltzmann distribution, where if you remember, the equation there was e to the negative change in u over RT. And here our change in u is activation energy. So since this is a probability, the exponential should be overall unitless. So the units of EA must match the units of RT or kBT, depending on which one you use. As you can see from the term itself, you have a, so there is a negative sign. So the probability would increase when the numerator is lowered or when the denominator is increased. Since R is a constant, you can only affect EA, activation energy or temperature. So when activation energy is lowered, the probability of finding a molecule above the activation energy would be greater. And when the temperature is raised, the probability of finding the probability of finding a molecule above the activation energy is also higher. This makes sense intuitively because if you look at temperature, it is the average kinetic energy. So if you have a higher temperature, you have more molecules at a higher kinetic energy on average. And since you don't affect the activation energy when you're changing temperature, the higher average kinetic energy will be you will have more on average, you will have more molecules on average above the activation energy. So a couple ways to influence the activation energy are with catalysts, which would decrease the activation energy. And then the pre-exponential constant is the A in front of the exponential term. So this the pre-exponential constant measures the rate that molecules collide and have the correct orientation. So it's really made of two parts. So it depends first on the rate of collisions overall. So not collisions that have sufficient energy or correct orientation, but just overall all the collisions possible. And then inside of that, it would be inside of the pre-exponential constant, it also depends on the probability that molecules will be in the correct orientation. So this means that the more complex the reaction, say it's like a 3 molecules colliding versus 4 molecules colliding, the probability that you'll have 4 molecules in the correct orientation should be lower than the probability you'll have 3 molecules in the correct orientation. Alternatively, since molecules are not necessarily spherical, if they have different geometries, that can also affect the probability that the molecules will be in the correct orientation. And then for this course, we assume that the pre-exponential constant will not be temperature dependent, and that the range of temperatures that we're usually using are not great enough to actually influence the value of the pre-exponential constant. So the units of this pre-exponential constant would match the rate constant, which for a first order reaction would be the reciprocal of second, so second -1. So the pre-exponential constant would also be with the units of second to the -1, and then for a second order reaction, it would be 1 molar to the -1, second to the -1. Okay. And then for this question, we are looking at an Arrhenius plot, and to get the equation that describes the Arrhenius plot, you would take the natural log of both sides and then separate the right side into what you see on the screen. You can see from here that you will have the constant, the pre-exponential constant by itself, which will be the constant term, and then you'll have something that depends on 1/t. And then you'll be able to use this to solve question 3. Does anyone have any questions?
So you said that temperature kind of like raises the probability of going over the activation energy barrier. I remember he discussed in class something about entropic barriers kind of not making this temperature statement always true. I'm just wondering what you have to say about that, or is it for the sake of time you can move on? I'm just wondering.
So yeah. I don't think I know enough to comment on it. Do any of the other tutors want to?
There's always an entropic barrier to the reaction. And by convention, we focus on the energy here. Actually, in biochemical reactions, the entropy is a very important part, and it's captured in something called the pre-exponential, which multiplies this. I think that's a level of detail you don't need to worry about right now, but entropy is always very important when the energy term, so it's really the free energy that gives you the probability of being at a certain position, and the free energy is the energy change minus T delta S. So the energy change is huge, like in chemical reactions where bonds are broken. The energy change is huge, so the entropy change doesn't contribute much. And in an Arrhenius kind of analysis, we're ignoring the entropy change. But in biochemical reactions where the energy of if the energy of whatever is happening is not very large energy change, then the entropy can become dominant.
Okay, thank you.
If no one else has any questions, we can move on to the actual question.
Okay, can everyone hear me and see my screen?
Yes.
Okay, so for 3A, it says that carbon-14 is an important isotope for the dating of organic samples by using the first order decay of its radioactivity as a fraction of total carbon. Suppose that carbon-14 has a radioactivity of 20 units per gram and a half-life of 5,200 years, and you find an artifact possessing 4 units per gram of radioactivity of carbon, and we're asked to calculate how old the sample is. So we're told that this is a first order reaction, which means that we can use the integrated rate law here and the corresponding equation to find the half-life. And we're told that the half-life is 5,200 years. The initial concentration is 20 units per gram, and the current concentration is 4 units per gram, and we're told to find the time. So we pretty much have everything we need to solve this here. We just need a way to relate the half-life to the general integrated rate law. So the first thing that you can do is solve for the rate constant using the half-life equation. And just as a sanity check, what units do you expect for the rate constant here?
Concentration per second.
For the rate constant though, not the rate.
1 over S.
Right, it should be 1 over time because we have the half-life in years and we're dividing by that to solve for K, which makes sense for a first order reaction. And then once you've solved for the rate constant, you can plug it into the integrated rate law to solve for T. Are there any questions here? Okay. So then moving on to part B. Imagine that you're studying an uncatalyzed first order reaction using an Arrhenius plot, and you have a line and 2 data points from that line. And we're asked to calculate the activation energy and the pre-exponential factor for this reaction. So as we just heard from Michael, we can use the Arrhenius equation, K equals pre-exponential factor times e to the power of negative activation energy divided by RT, which we can, if we take the natural log of both sides and rearrange some things, we have this equation, which is pretty much just an equation for a line that's described over here because we have y is ln k, the x-axis is 1 over t, so then we have the y-intercept as ln of a and the slope as negative activation energy divided by r. So we can use these 2 points to find the slope, which we can then use multiplied by r in order to find the activation energy. And to check for units, we have the units of the slope are unitless y over 1 over t as the x. So that becomes 1 over inverse Kelvin. And then on the right-hand side, we have activation energy divided by R, which has units of joules per mole per Kelvin. So you know that the units for the activation energy are joules or kilojoules per mole. And then to calculate the pre-exponential factor, once we have the activation energy and we also have a point, we can plug in those values. So we can plug in 1 over t as the x, ln k as y, and the activation energy that you would have just calculated into the Arrhenius equation in order to solve for A. And the units, so again, as Michael told us, because the exponential term won't have any units, the units of pre-exponential factor have to match the units of the rate constant. And in this case, because we have a first order reaction, the units of the pre-exponential factor should be inverse seconds. So are there any questions here?
So do we change years to seconds for our units? Will that always be the case?
You don't have to.
Okay.
Because
So
your final time that you're calculating is also going to be in years. I mean, you could change it to seconds, but it would be a huge number.
Yeah. Okay.
Yeah.
Thanks.
Mm-hmm. Anything else? Okay. For the next part, it says that an enzyme accelerates the rate constant by 10 over the uncatalyzed reaction by perturbing the activation energy. And we're asked to calculate the difference in activation energy at 300 Kelvin. So just to put this into an expression, we have that the rate constant of the catalyzed reaction over the rate constant of the uncatalyzed reaction is 10, because it's 10 times faster when it's catalyzed. And again, we have our Arrhenius equation, and we can define, so we're asked to calculate the difference in activation energy, which we can write out as the activation energy of the uncatalyzed reaction minus the activation energy of the catalyzed reaction. You could also go the other way around. It'll just work out nicely if we have it this way. So if we plug in the Arrhenius equation for each of our rate constants, we have this expression where basically everything is the same except for the activation energy for the catalyzed versus uncatalyzed version. And our pre-exponential factor stays the same, so we can cancel it out. And then we can rearrange the left-hand side because we have the same base. We can subtract the exponents. And if we simplify this a little bit more, we can see that the numerator of this exponent is exactly the same as what we defined as the difference in activation energy. So we have that e to the power of the difference in activation energy over RT equals 10. And we can rearrange this a little bit more to get that the change in activation energy equals RT times ln of 10, which gives us a really clean way to calculate the difference in activation energy. Are there any questions? Okay. And moving on to the last part of this question, it says that the activation energy of the enzyme is less than the activation, or enzyme catalyzed reaction is less than the activation energy of the uncatalyzed reaction. How does this change the spontaneity of the reaction? What are your thoughts on this? Can we relate the spontaneity of a reaction with its rate? So if we look at a reaction coordinate diagram where the x-axis is the progression of the reaction and the y-axis is energy, we can see this part is the activation energy. So the taller curve is the activation energy of the uncatalyzed reaction, and then the smaller curve is the activation energy with the enzyme. However, this doesn't change the energy of the products relative to the reactants, which is the delta G, which is what dictates the spontaneity. So this means that the activation energy is related to the kinetics, but you can't necessarily say something about the spontaneity of the reaction. You have to look at delta G for that. Are there any questions? And are there any questions about any other parts of this question that we previously discussed? If not, then we can keep going.
Hi, everyone. Give me 1 second to get my camera ready. Come on, work. Can everyone see? Is this clear enough for everyone? I can't seem to zoom in for some reason, but
Yeah, it looks good.
it looks good. Okay, thank you. So I'll be going over problem 4A on the problem set, and we'll be going over some concepts that go with these problems. So first question in problem 4A is asking us what is meant by the steady state condition for the reaction scheme shown above, where we have what you've seen in lecture, DNA going to mRNA by some rate constant Kr, and then down mRNA being degraded by rate constant K inverse R, K negative R. So what's the difference between, basically what's asking, what's the difference between the equilibrium and a steady state condition? So let's talk about equilibrium first. As you're all familiar with, I'm sure. Equilibrium, we usually are talking about some sort of reversible reaction, right? So we have something in the scheme, something like this. We have a forward rate, K1, a reverse rate, K negative 1. And we know as well that our change, Gibbs free energy, is 0. And how is that going to be different from steady state? In steady state, we have that concentrations aren't changing, right? So they're steady. Concentrations don't change. But we have a slightly different scheme usually when we're talking about something that's steady state, which is similar to what's shown in the schematic, where we have a multi-step process. So A is being converted to B, which is then being converted to C. And we have some rate constants here. And what steady state is saying is that this intermediate here, the change in this intermediate over time will be 0, meaning this rate 1 going from A to B will be equal to rate 2 going from B to C. We can also say something that that at steady state, at steady state, we have this rate where the rates are balanced, but they're not necessarily at the equilibrium concentrations. So that's another difference as well. We may not have delta G that's equal to 0. So for problem 4a, part 1, you can talk about any of these factors. Just explain clearly what's the difference between steady state and equilibrium. Any questions about that? Any comments about that? All right, then, let's move on to part 2. Part 2 is asking us, under the steady state conditions, derive an equation for the relationship between NR steady state, which is, in this case, the mean value of the number of RNA molecules per cell, and the 2 rate constants. So let's go back to our reaction scheme here. We have ND DNA molecules in the cell, and R RNA molecules in the cell. And we said in steady state, we have this intermediate we're looking at, which in our case is mRNA, right? We're saying that change over time will be 0. So change dNR dt should be 0. Meaning the rate of production of mRNA and the rate of degradation of mRNA should be equal, right? So we can simply write that as, excuse me, we can write that as ND, their steady state, times that forward rate, Kr, minus, because it's, so this is forming, right? Forming, we're subtracting the degradation rate. And R SS, K inverse R. We can rearrange this equation pretty simply, pull this over to the left side, and R steady state K inverse R, D steady state KR, and just solve this for NR. Pretty straightforward, right? Any questions about that?
So does NR stand for the number of, I guess, RNA molecules, or what's going on with that?
Yeah, so NR, as it says in the problem, you can look with the brackets here, or I guess these are called brackets. That's standing for the mean value of number of RNA molecules per cell.
Okay, cool.
Yeah. Any other questions? Okay, then I'll move on to part 3, which we're going to be utilizing that same equation from before, which is, all right, you can all see that. So part 3, I'll write it out one more time. ND steady state KR K inverse R. So now it's asking, what is it asking? Suppose that the rate constant for RNA production is 100 seconds inverse, rate constant for RNA degradation is 10 seconds inverse. What is the expected mean value of RNA molecules per cell? So it gave us the rate constant for RNA production, which is KR, right? Look back at the reaction scheme, that's 100 seconds inverse, and degradation will be the other one, 10 seconds inverse. Now, we weren't giving anything for the number of DNA molecules. And what we can view this as is we're asked to find the mean number of RNA molecules per DNA molecules. This was introduced in your class when we're talking about bacteria, right? Which usually has one circular loop of DNA within it. So we can treat this value, ND, as equal to 1, because per cell, when we're talking about asked to find RNA molecules per cell, each cell should have one DNA molecule. So using that assumption, just plug in. So our ND becomes 1. I'll just leave it there so you know. Plug in these values, 100 divided by 10, should get 10 molecules of RNA. And that is part 3. Are there any questions about any of the math I did or anything about steady state versus equilibrium? All right, take that as no, and then we can move on to Poojan, who will go over the last part of the problem 4.
Could I ask one more question before we continue?
Yeah, go ahead.
So steady state condition is basically saying that the intermediate is held constant, even though what's going in or what's going out is not necessarily constant.
Yeah, so our concentration of B, or number of molecules of B, whatever you're looking at, that is going to be constant over time. This and this, these may be varying. We don't know. They might also be in steady state. But when we talk about steady state for some specific intermediate, yes, that won't be changing.
Okay, thank you.
Yes. Any other questions?
Yeah, so on James's, I think his name was James, but he also described equilibrium as like none of the molecules changing within the reaction.
Right.
Okay. Yeah. Okay.
Yeah, you can think of it that way as well, but remember there's also, we talk about an equilibrium concentration, right? So equilibrium is technically a different state than when we're talking about steady state. So we have certain concentrations associated with equilibrium, and equilibrium is like, if we put a bunch of different concentrations of molecules into a reaction, they would decay or increase on one side, depending on what you're looking at, to an equilibrium. So that's another way to think about that. Anything else? Okay, Poojan, you can take over.
All right, sure. So before I get started with the problem solving aspect of 4B, I want to give a brief bit of concept review. So I'll start a little bit with probability distributions, and I'll go over the derivation of PNR, which was done in class, and then we'll talk about the Poisson distribution. So with that said, let's just get right into it. So first of all, what is a probability distribution? So in this class, you've already seen one example of a probability distribution before, and that's the binomial distribution. And this was mainly talked about in the context of calculating multiplicity. So when it was first introduced to you, it was this idea of, let's say you flip a certain number of coins. So if you flip, for instance, 100 coins, you might get a curve that looks something like this, where on the x-axis, the outcome variable is the number of heads that you get. So on this part of the graph, this corresponds
Poojan,
to...
I think you need to flip. For some reason, we're seeing your face rather than the.
Oh, okay.
Rather than what you're drawing. Yeah, that's much better.
Oh, okay, okay. All right. Cool. So yeah, like I was saying, this corresponds to the probability distribution of doing something such as flipping a coin 100 times. So you can see here that if you have a very few number of heads, like a very small number of heads, then the probability of that is pretty low, because if you flip a coin 100 times, you get 10 heads. That's a very not probable outcome. However, something more kind of in the middle of the road, like 50 heads, if you flip the coin 100 times, that's what's going to have the highest probability. And that's given by this curve here, and it's described by this equation right here. So I'm going to wait for the camera to focus a little bit, but in case you can't see it, it's the probability that you have k heads is equal to n choose k times the probability to the power of k times 1 minus the probability to the power of n minus k. And because this is coin flip, the probability is just 1/2. So this term right here would be 1/2 to the power of n. However, what we want to do for the context of problem 4 is we want to find a probability distribution for the number of RNA molecules at steady state. So this means that you're in a given bacterial cell, you'll give it some amount of time to produce some mRNA molecules, some of those mRNA molecules to get degraded, but at some point, the amount of new mRNA molecules coming in is equal to the amount of mRNA molecules that are getting degraded, and that's the steady state condition. So what we're interested in is knowing what the probability of encountering, say, like what's the probability that you only have one mRNA molecule at steady state, or 2, or 3, or 4, or any number. We basically want a distribution that can characterize that. So in class, this is what was introduced as sort of a model to approximate that. Hopefully you can see this, but essentially, if we're thinking about a hypothetical state NR over here, we can think about the probability of getting to the state as essentially a function of the probabilities of its two adjacent states. So for instance, here, the two processes that are important are mRNA getting transcribed from DNA and mRNA getting degraded. So naturally, the two states that we'd be interested in are the state where you have just one below the number of mRNA molecules. So for instance, if NR were, say, 10, then this would be corresponding to having 9 mRNA molecules. So with this rate KR, you can reach 10. Similarly, if you already had 11 mRNA molecules, you can have 1 get degraded and get back here to get 10. And so if we're interested in seeing how the probability of having a certain number of mRNA molecules changes, it's given by this equation here. And I can briefly explain where each one of these terms comes from. So this term right over here, this comes from the probability of having, of being in the state where you have 1 less than the one that you're interested in, times the probability, or like the rate of DNA being transcribed to mRNA. And then here you have the number of mRNA molecules that's 1 more than what you like, and the probability of degradation happening. And of course, the probability, the rate at which degradation occurs is related to the initial concentration that you have. Because say if 2% of your mRNA molecules are getting degraded per unit time, then it's much more likely to go from 100 to 99 than from, say, 5 to 4. And then here, this term represents going from this state where you have exactly n molecules, and then either having degradation go in this direction or having new transcription. And so with that, we can now consider steady state. So actually, one comment that I like to make on steady state is that here we are just describing the change in probability of the entire probability distribution as a whole. However, if we have a steady state condition, then that means that the probability of seeing exactly 10 RNA molecules, or the probability of seeing exactly 11 molecules, stays the same, which means that the flux between like these two compartments or these two compartments, that should be the same. So at steady state, what we should expect is that the number of mRNA molecules that's changing between these two states should be 0. Basically, there should be no change. Now, that doesn't mean that there's no transcription or there's no degradation. It just means that the rates are equal. So for that reason, now we can just consider one compartment alone. And like we said, at steady state, there's no change in the probability of the mRNA molecules. If we're only considering our state NR, we're now only interested in just 2 processes, which is, first of all, transcription from the state right before, because we're only considering them in pairs, and then also degradation from the current state. And then if we just write out these equations, this is again given the steady state assumption, which is that since the change in mRNA molecules is essentially 0, then the rate at which you're losing mRNA molecules from your current state is balanced by the rate at which you're gaining them. And then if you do a little bit of algebra, you'll eventually arrive in this form. And then since this is kind of like a recursive definition, you can back solve this all the way to your probability of having 0 mRNA molecules. However, this still poses somewhat of a problem because we don't have a value yet for the probability of 0 mRNA molecules. So we can do a little bit further math. And sorry if this is a little bit blurry, but a lot of this information is on lecture slides, which I can link as soon as I'm done talking here. But essentially, we know that for a given probability distribution, all the probabilities have to add up to 1 because we're working in an outcome space. So all the events together, they have to add up to a probability of 1. Since if you're flipping a coin, you can get either heads or tails. There's a 1/2 probability of each. There's a total probability of 1. So we know that if we take the summation over all possible values of NR, which is from 0 to infinity, we know that these probabilities will eventually add up to 1. We know that the probability of 0 is a constant term, so we can pull it out of the summation over here. and then we can divide by the entire summation to get this expression. And the note in your lecture is that this expression is very similar to essentially the Taylor expansion for an exponential of e to the x. So because of that, we can replace this entire we can replace probability of 0 with e to the negative kr over k minus r. And so this is the final expression that you arrive at in lecture. And the reason why this is very significant is that this is essentially the Poisson distribution. And so the Poisson distribution, the general form of it is given by this, where you have a parameter lambda, and your probability of seeing, let's say, 10 would be lambda to the power of 10 e to the negative 10 over 10 factorial. And so now I want to talk a little bit about the interpretation of the Poisson distribution. So first of all, let's talk about where the Poisson distribution comes from. Actually, it's very closely related to the binomial distribution. In fact, if you take the limit of the binomial distribution as n approaches infinity, you will eventually end up with this term here if you make the substitution that lambda is equal to n times p. And the reason why the Poisson distribution is very special is that it's useful in cases in which you have a very low probability event, but you have a very large number of trials. And a good example of this is, say you're randomly choosing one car in all the streets of San Francisco. You randomly pick one car. What's the probability that that car will be involved in an accident today? So the individual probability of an event like that might be low, but as we all know, we can observe accidents every day. So we know that these things do happen. So even though you have a very low probability of something happening, because you have such a large number of trials, you can actually see the outcomes of it. And in our case, we know that lambda is kr over k to the negative r. And the reason for this is if you look at the expression that we recently derived, or the one that you derived in class, here, instead of having e to the negative lambda, you have e to the power of negative kr over k negative r. So essentially, in this case, your lambda is kr over k negative r. And also, as discussed in class, there are some pretty interesting properties of the Poisson distribution. So the first being that the average is going to be equal to lambda, which in this case is kr over k negative r. And as you saw in part 4a of this problem, this is equal to the steady state number of mRNA molecules. Additionally, the standard deviation of this distribution is the square root of lambda, which would be the square root of this value as well. And so if we wanted to find what the probability of getting an mRNA copy number of K is, so for example, if you're interested in asking the question, if I pick a random bacterial cell and I want to know what's the probability that it will have exactly 4 mRNA molecules, 4 strands of mRNA of a particular gene at steady state, it would be given by this expression where you can just sub in 4 for K. So that's just the kind of brief introduction to the Poisson distribution. Does anyone have any questions about that before we go to the problem? Okay, so that's it. I'll get right into part B. So for part B, number 1, okay, I'll let the camera focus a little bit. Okay. Okay, I hope that shows up. So for the first part of this problem, we're interested in knowing what is the probability, where we want to show that the probability of the bacterial cells in the population having a copy number of mRNA different from the steady state number. We want to show that this probability is more than 0.8. So essentially our goal is to show that this probability that NR is not equal to our steady state number is going to be greater than 0.8. So instead of calculating the number of mRNA molecules where you have 1, 2, 3, and all of them except the probability of having exactly 10, which we found was our steady state value, what we can do instead is take the complement of this probability. So essentially what we're saying is that this probability that NR is not equal to 10 is equal to the probability of 1 is equal to 1 minus the probability of having exactly 10. So if you solve this expression, the probability of 1 minus the probability of having exactly 10, you will get your answer. And you're given the Poisson distribution right here as we derived in class. So just to make that explicit, the expression that you want to solve is this. And because it's mentioned that you want to use the same rates that were mentioned in part A, you can plug in KR and K minus R into that expression. Hopefully that's clear, but I guess I'll just read this aloud. This is 1 minus e to the negative kr over k negative r times kr over k negative r to the power of 10 times 1 over 10 factorial. Okay, any questions so far? Okay, so now on to the last part of this problem. So here's a graph of the Poisson distribution, and we're told that this corresponds to a certain population of cells. Also, the setup in this question is that there is a certain antibiotic resistance gene such that if you have more than 20 mRNA strands of it, then you effectively have resistance to it. But as you can see from the probability distribution, this number is 10 right here. I know it's not super obvious. So this number is 10, 20 is all the way up here. So we're talking about a very minute population of bacteria that are expressing this number. And what we're asked to find is, if we have a population of 10,000 bacteria, how many of them will be able to express enough of the resistance gene in order to survive? So in solving this problem, we're asked to make one assumption right here, which is talked about in the note, which is that essentially, if we wanted to calculate the probability of, or if we wanted to calculate the number of bacteria that are going to survive this, it would essentially be the number of bacteria times the probability of having 20 mRNA plus 21 mRNA plus 22. However, since these probabilities beyond this point are so small, we're essentially assuming that the probability of having exactly 20 mRNA molecules is equal to having all the probabilities from 20 to infinity mRNA molecules. So again, the solution to this is going to be very similar to what we did in the last part, which you had your formula for P and R. And essentially what you're going to be doing is you just want to sub in NR equals 20. And of course, you're going to use the same K negative R and KR from part A. And then once you find this P and R, so I'll just denote that as P20. So once you find P20, you want to multiply that by the number of bacteria that you have in your population, which in this case it's mentioned as 10,000, because if you're given that the probability of having more than 20 mRNA strands expressed is something like 0.005, you just multiply that by 10,000 and that will give you the total number of bacteria that you can expect to have more than that expression level. Okay, so I think that pretty much does it for question 4B. Does anyone have any questions?
Are the rate constants the same with the previous question?
Yeah. So so I think it's mentioned like 100 and 10. Yeah. So you can use 110.
Okay. Thank you.
All right. Well, if there are no further questions, that's the end of all the planned material that we have today. So we'll still hang around for a few minutes if you have any questions. Just feel free to either type them in the chat or just ask us.